Okay, so good morning. We have about 1 minute. So in the last class, we were looking at block ciphers. Okay, so especially I started with the affine cipher, which is of the form ax plus b, right? If x is a plain text, then ax plus b is the encrypted text for the key a comma b, right? And we also talked about a couple of other ciphers. Today, I'm going to do first stream ciphers. So the difference between block cipher and stream cipher. So in block cipher, for each block, the key is same. Here actually, we have the key is different for each block, and also there is a mechanism to generate the key. Okay, so key stream you can generate. So that is a really interesting thing. I'll talk about few things there. And finally, I'm going to give you cryptanalysis of affine cipher. How do we break the cipher, So some idea about it. It will be very, elementary thing. I mean, you will see that how we can actually break it. And obviously, I think one can write a program to break a crypto system, right? So, but what is the philosophy? How do we break a crypto system? That is very, very interesting. So we'll talk about it. So that's the plan for today. So I'm just recalling this is the crypto system, a 5-tuple, plain text, ciphertext, key space, encryption rule, decryption rule, right? Then we talked about shift cipher, we talked about substitution cipher, we talked about affine cipher, okay, and then Wagner cipher. In fact, you will see that this cipher is also a special case of stream cipher, okay. And we talked about Hill cipher, permutation cipher. So now we are ready with stream cipher. So now in the block cipher, if you see y is y1, y2, y3, and so on, it's so basically each yi is encryption of of xi, right? And the encryption same key is used, same key is used all across the data, right? All across the block, right? So if somehow we can generate different key, you see, if yi is encryption rule of zixi. So for each block, there is a different key. And we should know a mechanism to generate this key stream. Z is equal to Z1, Z2, Z3, right? So stream cipher. You can assume that a stream of keys is there. So if the data is coming, you can actually encrypt each block differently. So basically, key stream, the question is how do we generate the key stream, right? So first key difference, that from block and stream cipher, so obviously you see that the key is different in each block, right? So Z1, Z2, Z3, and there is some mechanism to generate this key stream Z1, Z2, Z3. Now key stream, if it is only function of keys, so you can generate key using some starting key pair that is synchronous cipher, right? Or otherwise, and no plain text. But in other cases, basically it is also a function of plain text and ciphertext. Okay. So if the key stream is a function of only key, only some keys, right? So then we call it as a synchronous cipher, otherwise asynchronous cipher, right? Where actually it is function not only of keys, but also plain text and ciphertext. Okay, some combination. So that is a key difference. So here is a formal definition of synchronous stream cipher. So it's a 6-tuple. P, set of plain text. C, set of ciphertext. Key, your key space, a finite set of possible keys. L is a finite set of key stream alphabet. Okay, because now we have key stream. And G, a key stream generator, some sort of function which is going to generate the key stream. So our task is to somehow generate that key stream Z is equal to Z1, Z2, Z3, Z4, and so on, right? we need to somehow generate the key stream. Okay, so let us see that. Obviously, for each Z in L, okay, all these keys are coming from L. L is the key stream alphabet. There should be encryption rule and decryption rule such that encryption of plain text will give text and decryption of ciphertext give you plain text, such that this condition is satisfied, right? So you encrypt and decrypt, you get the plain text, right? This is the common condition. Now, if you look at this cipher which we looked at earlier in the last class, Wagner cipher. So basically, this is a special case of this stream cipher. How do we do that? So basically, you see that PCL is same, Z26. Encryption rule is X plus Z mod 26. Decryption rule is Y minus Z mod 26. Okay. If we define key stream Z1, Z2, Z3 as Zi is equal to Ki from 1 up to M. So for the block of length M, its string is same as K1, K2, K3, right? That key is same thing as K1, K2, K3, Km, right? And then if it is more than M, basically we are actually repeating the same thing, Z of I minus M, right? So we are again getting K1, K2, K3, Km, and then another K1, K2, K3, Km, and so on. Okay, so this is coming as so this is a block, right? So you will get streams like this. So you can clearly see that Wagner cipher is nothing but a special case of stream cipher, okay, with this kind of function. So this is the definition. This is how the key is. Question is, so can we get all block ciphers as a special case of stream ciphers? Can we get all block ciphers as a special case of some stream cipher? Yes, if key is constant throughout, right? You will get the same, right? So as I mentioned, the difference is what? There, each block has same key in the block cipher. Here, each block has different key. So if the same key you use, you get the block cipher. Okay, so it's straightforward thing, right? So block cipher is a special case of stream cipher where Zi is equal to K for every I, right? Same. Now, when we have this infinite stream kind of thing, actually, for the key stream, so there are a couple of other things, interesting things. We can talk about periodic stream cipher. So periodic means if Zi plus D is Zi for every I, so that means we say that there is a period D, right? Okay, all these are the keys, right? So basically, now you can see that Wagner cipher is a periodic shift cipher with period M, because M block, the keys are same for each M block, right? For each size M block, keys are same, right? So periodic with period D. Now, basically the question is now how do we generate this key stream? Okay, so the Z1, Z2, Z3, Z4, Z5, Z6, and so on. How do we generate this key stream? And have you ever tried a SYN? SYN means trying to generate random numbers with computers. Have you tried? All good competitive programmers in the class? Have you tried generating random numbers? Actually, it's a sin. Paap hai. You cannot generate, right? Truly random number you cannot generate. It's a really very beautiful thing. आप नहीं कर सकते हो computer science में, right? So basically, do you know actually how do you actually generate? I mean, is there, you may use some Python function or library, that is I'm not worrying about. कैसे काम करता है? How do it work? Any idea? This is very important question for competitive programmers also, because interview में they may ask, how do you generate random numbers? Very basic question. Okay. Any idea? So there they use something what is known as linear feedback shift register. Have you heard of this term? linear feedback shift register, LFSR, right? It's a very common, popular thing. And actually, we are going to use a similar technique here for generating these key streams. Okay, so I love these linear feedback shift register. They are beautiful things. There are multiple things possible for that. Anyway, so what we do? So we assume now, actually now for simplicity, we are assuming that we are working for the binary Z2. Okay, the plain text, cipher text, and that key stream is coming from binary thing. Okay, and we are looking at periodic shift cipher. So sorry, periodic synchronous cipher. So what we do, encryption rule is x plus z mod 2 and decryption rule is y plus z mod 2. Now, how do we generate, the method for generating the key stream is, so we assume that this is our starting point, K1, K2, Km, right? So initially, Zi is Ki from I is equal to 1 to M. So Z1 is equal to K1, Z2 is equal to K2, Z3 is equal to K3, and so on. Zm is equal to Km. The first initial block is this, right? And then for next onwards, this is this kind of combination. This is a very beautiful combination. Summation 0 to M minus 1, Cj plus J mod 2. Okay, this is known as linear recurrence of degree M. I think in discrete math class, somebody might have taught you linear recurrence relations. I don't know. मैंने किया था क्या? I don't remember. You might be remembering anyway. So linear recurrence relation is something really interesting. So basically, the period here is length. So basically, length is 2 raised to power m minus 1 in this case when you use this kind of expression. And there are different ways you can visualize this expression. So let me show you. As an example, suppose m is equal to 4, and this relation is zi plus 4 is equal to zi plus 1 mod 2. Very simple thing. So if k1, k2, k3, k4 is any non-zero vector, okay. So basically we are saying this is the seed which we are starting with. You can see that z1 is equal to k1, z2 is equal to k2, z3 is equal to k3, and z4 is equal to k4. Suppose it is something like 1 0 0 0, our initial seed, right? Then what will be the key stream? So this is k1, this is k2, this is k3, this is k4. Essentially this is z1, z2, z3, z4, right? And now this one is from that formula. What is this value? Z5. I is equal to 1 means Z is equal to 5. Z5 is equal to Z1 plus Z2. Right? So I'm just summing. This is Z1, this is Z2. So 1 plus 0 is 1. We are getting this value. Right? Then the next one again from that formula, you can compute. This is Z6. Right? And Z6 is sum of Z2 plus Z3. So Z2 is 0 and Z3 is 0. So 0 plus 0 is 0. And like that you can generate. Right? Got it? So Z6, for example, this is Z15. You can compute Z16, Z17. This is very fairly straightforward thing. You will see that so this thing is periodic with some period. As I mentioned, the period is 2 raised to power m minus 1. That is the thing after which it will start repeating. Actually these things are, have you heard of cellular automata also? Some enthusiastic people might have heard about it. There is a very nice book to padhte nahi hoge, right? So a new kind of science by Wolfram, right? I think it is available in the library. I have ordered it long time ago. It must be there. Huge book, You will observe the beauty of computer science and mathematics. The person was physicist. Wolfram, I just had one dinner with him, long time ago. So he's the founder of Mathematica, by the way. So, he has spent his time in studying about this physics. How do we do this? And then he implemented this. He had this passion for programming, so trying to simulate these cellular automata, and that resulted finally in the whole Mathematica business, right? You see, the beauty of math can give you money also, right? So anyway, so cellular automata also has this kind of behavior, right? Depending on what seed you take, different behavior is observed, right? Sometimes it is periodic, sometimes it is, purely chaos, you can generate all kind of things, So when this happens, how this happens, you can study. So actually the similar kind of things are here also, in this kind of behavior, right? We want to generate the key stream, right? When it will be periodic actually, So that is something very, very important, right? So anyway, so this is something example about this key stream. So this is, so another basically understanding of it is linear feedback shift register. So we have, this, that initial seed is here, and then there is a feedback, right? And then you keep on generating the stream from here. So this is the shift register. This is known as shift register. There is a very nice book by Golem, S.W. Golem. I don't know, you've never heard of these people, right? That is also, I mean, you can search. So whatever I'm saying, that you can look for these people, right? Golem has written a very nice book about these things. And actually, he has studied why these sequences are very, very important. They are useful in diverse applications. For example, CDMA technology, right? Who uses CDMA technology in India? Who used CDMA technology first in India? Reliance only, right? Sometime back, if you remember. So you are not studying general awareness is also less, right? Anyway, so it's very interesting thing. So you know, uh, so code division multiple access communication, CDMA, where actually a lot of people are talking. It's like that a lot of people are talking in the room. So how do make sure that there is no chaos, right? I mean, nothing will be, uh, you know there is no kind of chaos. So basically, you can generate some binary sequences, or even quaternary sequences. So basically, these kind of sequences generation depends on these kind of techniques, linear feedback shift register or something like that, or there are other kind of techniques in mathematics. Anyway, so here this k1 k2 km is a the initial thing. So k1 would be topped as the next key stream bit, and k2 km would each be shifted. One is one space to left, and new value of km as this combination summation z is equal to 0 to j is equal to 0 to m minus 1 cj kj plus 1, right? So this is the technique of LFSR. Okay. So as I mentioned, synchronous cipher, when the key stream is function of only keys. And now when it is function of, in addition to keys, it also function of plain text or cipher text. It is known as non-synchronous stream cipher. Okay. Yeah. So that's all. Really not very difficult. So there is an example is auto key cipher. So Z1 is equal to K. So PCKL is Z26. Z1 is equal to K, and Zi is equal to Xi minus 1 for every I. So now, and encryption decryption rules are like this. This is known as auto key cipher. I think this is the last question in your assignment number 1. If you have looked at the assignment 1 till now, right? The last question is on auto key cipher. Linear feedback shift register. So I think that equation, which I showed to you, yeah. So that is very, very important. How do we form those equations? So yeah, so I mean, just work it out. I think solve that equation. So that's why I'm saying that just give the seed and see what happens. Okay, give the initial seed and see what happens. You write it down. Chai ka cup chahiye hoga, right? You just do it. This is for auto key cipher actually, right? K is equal to A. Plain text is this. This is the mapping, and then now you see that if K is 8 and this is your plain text. So plain text is used as a key stream 17, 4, 13, 3, 4, 25, 21, okay, 14, 20, like that, right? So basically you do the you are using this. So basically key stream is function of not only key, which is k is equal to 8 here, plus in plain text here, right? So key stream is like this. Then you get the encryption, and then you can do all these things are simple, right? Encryption, decryption is a straightforward thing. So I think now this is all about couple of examples of block ciphers, right? So we talked about block ciphers and stream ciphers, the basic understanding. So if this is enough, now let me show you how do you break a crypto system, and that is an art, right? So if you can break a crypto system, you can make a lot of money, right? So there are many techniques. Have you heard SQL injection, by the way? Popular term, but anyway, that's something else. But anyway, so breaking a crypto system is a very interesting thing. Maybe you should try once. So let me look at the cryptanalysis. How do we break a fine cipher? A fine cipher. So rule is encryption of X is equal to AX plus B. A comma B, the pair is a key. And how do we break it? So the question is, how do we break it? Any idea? So then you can see for solving any problem, whenever you encounter any problem, one habit you should have is the, I mean, that habit is observation, right? Observation is a very important thing. I think these days we are losing attention span attention, right? You don't observe things. So you observe nature, you will find solution. You observe something, or if the data is there, you observe the pattern, right? That is very, very important. So we are going to use one technique. So basically, if you are assuming, if you are working on English alphabet, so I'm going to use some properties of English text. So I give you as an exercise the same technique for Indian languages. It could be Sanskrit. It could be, what are the other languages? Gujarati, Bengali, Marathi, whatever you take. And so, you will take English alphabet. I will take probably make crypto system using Sanskrit or maybe Gujarati, right? So how will you break it? Right. So here I am showing you the, something for English. Okay. So what we are looking at is the following. So as I mentioned earlier, there are a couple of attack models. So ciphertext attack. So you ciphertext somehow and you want to break the thing, right? Or known plain text attacks. The opponent possesses a string of plain text and a ciphertext. So you want to break the crypto system. Or chosen plain text attacks, right? The opponent has obtained temporary access to the encryption machinery. Hence, he can choose a plain text and construct the corresponding ciphertext. Chosen ciphertext attack. The opponent has obtained temporary access to the decryption machinery. Hence, he can choose a ciphertext string Y and the corresponding plain text string X, right? So I'm right now focusing on known ciphertext attack. So opponent possesses a string of ciphertext that we have. Now I have to break it. Okay, how? How we are generating that thing. So here is the property, statistical properties of English. So remember, I have asked you find out the statistical properties of all the Indian languages, right? Sanskrit, Marathi, Gujarati, whatever you are good at Gujarati languages mostly probably. So you can find that statistical properties, right? And any Indian language. So in English we have this. By the way, so this table will not work before 1600, right? Remember, I told you there were only 24 alphabets. This table will be different by then. Anyway, so these people, Baker and Piper, actually gave this analysis, statistical properties of English. So if you observe any written text in English, this is the probability of occurrence of each letter. So so you can see that which one is the highest probability? E, 0.127. And this properties was exploited also in one more thing. Remember, discrete math class, which encoding technique we have used this? Huffman coding, right? Huffman coding, we use these properties, right? Because E, you can use less bits, right? So you can actually compress depending on what kind of things are there, right? This is very, very important. So this is statistical properties of the language. So I think I'm inviting you again and again, I'm telling you. So maybe I can ask this in the exam also, right? So, for any Indian language of your choice, give me the statistical properties. You have the internet, search, and see if you have something right. So this is something interesting. So now E is highest probability. So I mean, these are some observations. E is having probability about 0.120. Then next one, these letters T, A, O, I, N, S, H, R, each is having probability between 0.06 and 0.09. Okay. D and L each having probability around 0.04. C, U, M, W, F, G, Y, P, B each having probability between 0.015 and 0.028. And finally, so these are the least occurring things, right? V, K, J, X, Q, Z each having probability less than 0.01, right? I think there are the similar kind of properties you can also look at in the names. See, if there are so many people in the class, if I ask, most probable the girl name will start with S, probability wise, So you can observe these kind of behaviors, in any collection. These are the statistical properties, of names or English, something which is very, very common. So basically you can guess things, based on. So basically these kind of observations. So this is an observation, right? Based on these observations, you can try to break the crypto system, right? So let me show you. Another observation is about diagrams and trigrams. What are diagrams and trigrams? The 30 most common diagrams are T, H, H, E. So, two letters taking together, T, H, H, E, I, N, E, R, and so on, These are the most common diagrams, and 12 most common trigrams are T, H, E, I, N, G, and so on. Similarly, you can have for length 4 and so on and so forth, right? So basically, these observations of the English text will be useful for breaking the crypto system. So I'm going to use the first table, the statistical table, to break the affine cipher. I'll show you how you can break the affine cipher. It's very simple. Okay. So cryptanalysis of affine cipher. So suppose ciphertext is given. Obviously, I cannot read F, M, X, V, D, E, D, and so on up till RH, right? This is a ciphertext obtained from affine cipher. So we know that the person is using affine cipher, and the encrypted text is this. How do we break it? So what you do? Just take a cup of tea and observe, right? Take a cup of tea and observe this. So you can count frequency. So the first observation, the length of the encrypted string is 57. The size of the string is 57. Fine. And now we can look at the frequency of occurrence of 26 ciphertext letters. A will occur twice. You can see that tick I have made. A here. A is occurring twice. B is occurring only once. Where is B? That is B. C is not at all there, right? So I can just make this table. Simple observation. What is the length? Number one. Number two, occurrence of each letter. Make a table. And suddenly you can write a small computer program to do this, right? It's very easy. Just write down everything. Now what you do? Now what I should do actually? Tell me. How do I break? So you know the statistical properties of English and you know the occurrence of letters in this encrypted text. Now what you should do? Any idea? Yeah, so of course I have looked at the frequency right here. Which one is the maximum frequency here, by the way? R. Very good. So most likely R is E. Very good. Right. This is how you proceed, right? Just match the frequencies, right? So R is the most frequency occurring thing here. So probably E, because E is having more probability, so R should be mapped to E, right? So that means we have this equation here. I'm writing these guesses. Guess 1, G1 is guess 1. R should be E. And similarly, we can look at the second one, the most probable. D corresponds to T. Okay. Now that means what? Encryption of E is 4, 0, 1, 2, 3. Right? So E is 4, right? 0, 1, 2, 3, 4. 4 is the E. So encryption of 4 is 17, R, the value 17, right? In the mapping, and encryption of what is the 9? No, what is that? 19, yeah, okay. Yeah, 19 is 3, right? So encryption of 4 is 17, and encryption of 19 is 3. Now encryption rule is ax plus b. So I can write down the equation. 14a plus b is equal to 17, and 19a plus b is equal to 3. So you have got what? System of equations, right? Linear algebra. So basically, any problem will lead to bunch of equations. If you know how to solve equations, you are done. But now we are solving equations over integer modulo 26. It will not be so easy, right? How do we solve a system of equations over finite field? This itself is a big task. When you go to finite rings, it is much more difficult. But you can, this is a small case, so you can always, what you can do, plug and play, right, and see which one will work. By the way, I think you must be knowing that there was a nice equation. Square root of x plus y is equal to 5. Square root of y plus x is equal to 3. What is the solution? Square root of x plus y is equal to 5. Square root of y plus x is equal to 3. So square root of x, one term, plus y is equal to 5. Square root of y plus x is equal to 3. Right. So Ramanujan gave within half a minute answer by observation. That observation thing is very, very important, right? How do we get this anyway? So now we have this equation, so we can solve it, right? You will see that one solution is a is equal to 6 and b is equal to 19, right? You can plug in and see they satisfy the equation. But is it our actual key? So a is 6 and b is 19. Actually, it is illegal key. Why it is illegal key? Because the valid keys are having this property that GCD of a and m should be 1. Here GCD of a and 26 is 2. Because a is what? 6. So GCD of 3 and 26 is 2. Right? So it is not 1. All the valid keys should have GCD 1. Remember, affine cipher has this condition. Otherwise, the decryption rule will not work. So that means this key is not going to work. Right? So then we are again. The first one I am trying. The second guess is, now we go move. E probably is the T. We are changing the table, right? The next probable thing that will occur. E is T, and this gives you A is equal to 13. Again, illegal key. Because A is equal to 13, GCD of 13 and 26 is not equal to 1, right? You keep on doing like this. The third guess will give you R is equal to E and H is equal to T. Gives you A is equal to 8. Again, illegal, right? It's not going to work. Then you try one more. You keep on doing this. So basically, it's like exhaustive thing, right? So we have fixed the first one, and we are moving the second one, right? And keep on trying. Which one will give you the answer, right? If we can find some pair, then we are done, right? Which is a valid key. Then, if you take R is equal to E, so in the fourth guess, and K is equal to T, we get A is equal to 3 and B is equal to 5, and GCD of A and 26 is 1 now, right? Because GCD of 3 and 26 is 1. So that means this is a legal key. So we have found the key. A is equal to 3 and B is equal to 5. So key is 3 comma 5. So decryption is 9y minus 16, right? A inverse. This is A inverse, right? Which is 9 here. So it is, you can find, yeah, so decryption of y you find. So which is 0. So 0 corresponds to A. 0 to 25, right? ABCD mapping. 0 corresponds to A. That means so X is our A, right? That means we have this result here. So when Y was F, So we found the key. So basically we look at the first letter here, which is F. So Y is F. So we found X is 0, which is A. Right? So first letter we decoded correctly because now we know the function, right? 3 comma 5, right? That is our key. So we can compute, go to the next one, M. I can find, so if Y is M, I can tell what is X. Right? So keep on doing this for the whole thing and you will find, because we have found one key, right, which is working correctly. So it's kind of exhaustive thing, right? You know, you're not going to do this with hand. You can write a computer program which will actually do these things systematically, right? So should you, I mean, want to try this? I mean, do you want to write a computer program to do this? How long it will be? I mean, how large it will be? Maybe 200 lines, 300 lines, I don't know. So obviously people have written, those who are computer savvy or tech savvy, they have written computer programs too. Any question about this? How do we break? Any question? Hmm? How to do the cryptanalysis of affine cipher? Clear? Yes. Actually, that's a very interesting question. What happens when you are solving the system of equations, right? Uh, by the way, I think you must be knowing. I'm forget about system of equation. I'm saying that even if you have uh, degree 2 or degree 3 or degree n polynomial, how many roots are there over field? If there is a degree n polynomial, how many roots are there of, degree n polynomial? N, fundamental theorem of algebra. But over finite rings, it could be more. So degree 4 equation can have more solutions, maybe 5, 6, right? It's kind of bizarre world. So here, uh, you know, so probably you can then see actually, to answer your question, I found suppose two. I look at which one makes sense, right? The English, and I can say, okay, this is the thing, right? But otherwise, I mean, we don't know, right? Because we are, it's just an exhaustive thing, right? We are just trying to find a pair which works, and then you decrypt it, right? So in general, you are saying that what could happen, that there more. So your question is essentially in this mathematics of these equations, can we have more solutions? So you're right. That is a interesting thing. So thanks. You have given me a question for your quiz or exam, right? So how do we solve a system of equations over finite ring? Right. How will you solve a solution? Do analyze, because the finding rank is also a difficult task actually over these finite rings. So Z26, even if you fix those Z26 things are, so it's a beautiful thing actually, right? So look at it. Okay, so I think that's all for. So tomorrow I am going to, not tomorrow, on Friday, we are going to do the other cryptanalysis, because that involve, it will be more complicated. So we'll do it next time.